All right, so after the last video, if you feel like you got through that, then this one's going to be kind of you're going to see some similarities with this one. But we're going to go just a little bit further, which is why, by the way, it's called here Chapter 9 Extension, Pi bonds and isomers. So before we even get started, you definitely have got to know what the heck an isomer is. Compounds with the same molecular formula, but different structural arrangement of atoms. So catch that, same molecular formula, but different structural arrangement of atoms. This would be like two different teachers that have the exact same classroom and the exact same students, but they have their desks arranged in a different way, and so their classrooms actually look quite different. Okay, so that's an isomer. So moving on, these two things at the top of the screen, C2H2Cl2 versus C2H2Cl2, they can be different. And here's how. So one of them can be called cis, C2H2Cl2, and the other one can be called trans, C2H2Cl2. The full name would be cis 1,2-dichloroethene and trans 1,2-dichloroethene. Not that you need to know those, but if you're curious, the whole 1 and 2 thing, it's meaning that the chlorines are attached to the first and the second carbons, which you'll see in the structures here. Okay, so now as you look at these structures, do you see that they are different? What's different? Say it out loud. Be goofy. I'm talking out loud to myself. You do it now. Oh, yes, I do. I see that too. You see that in the structure on the left that the chlorines happen to be on the same side, where on the right side you've got opposite sides, that the chlorines are kind of top and bottom. So the designations that you need to know is that when you look at a structure, you would want to say that the structure on the left is what's called cis. And the way I always remembering was that cis and same start with the same S sound. That was a lot of S's right there. Cis and same sound. Trans is opposite sides. Like there's a transfer, or I think I've even heard some people even mention something about, transgender, that you're kind of, flip-flopping. I know that's a funny analogy, but if it works, then it works. So we're on opposite sides here. What this is caused by, like the way that this can actually happen, is what we were talking about with the last presentation, that when you have a pi bond, only one pi bond, because again, in this, the first bond would be, of course, your sigma bond, and then the second one is your pi bond. When you break that pi bond for a period of time, the whole molecule can rotate, and what that causes is the chlorine that was here on the bottom now flips up to be on the top and the hydrogen to the bottom. So you can get cis-trans isomers when rotation is possible around a double bond, which is what we have here. Ooh, rotation. Nice. I kind of want to see that again. You ready? Ooh, rotation. Nice. Okay, so how is rotation possible? Well, the structure that you see here, so is this cis or trans? What do you think? Cis, good. Okay, so the way that this can become a trans shape is by these pi bonds, and by the way, I've color-coded them so that you can see which one was originally on the top and the bottom. So you might remember originally I made it all green or all purple. So here, just color-coded so you can see. So here you can see both of the greens are on the bottom and both of the purples are on the top. Well, what's going to have to happen is the pi bond, which is between these two unhybridized p orbitals, must break. Ready? It broke. Ooh. Want to see it again? Okay, good. Ooh, it broke. Good. All right. So rotation is now possible because there's no attachment in between. There's no attraction. So rotation occurs and the pi bond will reform, but usually in the opposite orientation. So something like that. So now do you see how my color coding has switched? So this is now, considering that the chlorine is here and the chlorine is now here, that they are on opposite sides of the structure, that's now considered a trans structure. And now we can reform those bonds and we've made our trans structure that's kind of locked into place. So I say here in my bottom, the bottom little box here on the slide, lots of energy is needed to break the pi bond. Isomers from double bonds are not very common, but they can happen. So all you have to do is give it enough energy to break the pi bond, have it rotate, and then you can lock it back together. So cis and trans isomers can happen, okay? It is definitely a possibility. But when you take a look at the next thing, we're going to see a little difference. So again, not incredibly common, but it can happen. How about this? These are common. These cis-trans isomers are common. And I apologize here that my formatting got a little messed up. This is cis 1,2-dichloroethane and then trans 1,2-dichloroethane. So my apologies. But these are very common to have cis-trans isomers. Any thoughts on why? Oh, I think I heard a right answer. I think I heard somebody say, well, this is just a sigma bond. This is head-on bonding. There is no up above the bond and below the bond axis that's happening. And so we have head-on head or head-to-head overlap. And what that means is that there's no lock. We can freely rotate around this middle carbon-carbon bond. And that means that cis-trans isomers happen all the time. In fact, they're constant. Excuse me. In fact, they're constantly happening because there is complete free rotation around this bond. So again, hopefully that makes sense. So what's so important about cis-trans isomers, besides maybe being able to recognize them on paper and know what cis and trans mean? Well, here's the real deal. Properties. Isomers exhibit different properties. So the same cis-trans isomers we've been talking about the whole time here are dichloroethane. Notice that the cis isomer has a boiling point of 60 degrees Celsius, whereas the trans isomer has a boiling point of 48 degrees Celsius. Interesting. This means it takes more energy to get the cis isomer to vaporize. Right? It takes more energy. You got to put more temperature and more heat into the cis to make it actually turn into a vapor. Why? Think about it a second. Pause the video if you want to think for a second and think about why this could be the case. Okay, so let's talk about it. Cis structure has a dipole moment. Okay, do you see the structure here? See how the two arrows point in and then these two arrows point out? See that? As opposed to this one, do you see how this arrow points in and right across it points in, and then here this points out, and then straight across this points out? So in the cis structure, it has a dipole moment because these arrows are kind of all sort of pointing in the same direction. Individual molecules are attracted to each other because there is a relative negative charge on the bottom and a relative positive charge on the top. So because of that, these individual molecules will stick together. And so they're going to cause a need for more energy to actually cause them to vaporize. Whereas the trans structure, this individual or these individual molecules that are in the trans structure, they don't really attract to each other because you actually have a pretty nonpolar molecule right here, no net dipole, because the hydrogens are pulling and the chlorines are pulling in sort of an X shape, and that's sort of equal and opposite. And that's going to lead to no dipole moment, no attraction, which means that they will vaporize way easier. So an interesting application of cis-trans isomers. Again, you'll want to be able to recognize them on paper and know the distinctions, but what you see on this slide is really the most important part. So that's it. Quick one today. Yippee.